Welcome to the Transport Phenomena class. Today, we are going to talk about, in this session, the mechanisms of the mass transfer before we take up shell mass balances. So here we are seeing diffusivity and the mechanisms of the transfer. At the first instance, if you want to understand, then we have to go for the notation scheme. So number one is the Fick's law of the diffusion, which defines or which describes the movement of one chemical species A to a binary mixture of A and B because of the concentration gradient A. For the binary diffusion, we use the capital italic letters A and B. Suppose if I want to write the diffusivity, you know, of A through B, A into B, we write dA. There is one more definition called self-diffusion, in which diffusion of the chemically identical species is table take place. So this is actually given as D A star. Okay, moving ahead, we now come up to a build-up of the steady state concentration profile for the diffusion of the one substance A through another substance B. So here we are considering a thin slab and what you call a slab of thickness Y. Okay, this is a slab, and I'm showing this is a slab. This is a slab here. So thickness Y is considered to be as thickness of slab is considered as Y. Initially, the gas surrounding these two, or top surface and the bottom surface, is air. Okay, so this is the situation. Here, in the figure, what is it? The symbol WA, the symbol WA, or W subscript A stands for the mass fraction of the helium, and WA naught, you see here, WA naught stands for the solubility of the helium in the fluid silica, again expressed as mass fraction. So going ahead, uh, so what is that we want to show? So we are considering the thin horizontal fused silica plate of uh, area and thickness y, and at time t less than 0, I have shown you already. Both horizontal surfaces of the plate are in contact with the air, which we regard as a completely insoluble in silica. Now at time t is equal to 0, the air below the surface, the air below the plate, that means the air below the plate, the air below the plate is replaced with helium. That is at time t is equal to 0, which is appreciably soluble in silica. So what we are looking at is there is a plate like this, there is a slab like this. Initially, this was filled with air, but at time t is equal to 0, it is replaced with helium at the bottom plate. But there is some thickness here available. Now what will happen is this helium tries to diffuse through this slab and slowly reach the top surface, and it tries to replace the gas available above the plate also. Now you can see this the molecular transport of one substance unit to another is known as this. And see the helium slowly penetrates into the plate by virtue of its molecular motion here, and ultimately appears in the gas above. The air above the plate is being replaced rapidly so that there is no appreciable buildup of the helium there. So we just have a situation as a preliminary figure. So uh, as the and we take up the direction also here. Now you consider this here. So this is y direction and this is x direction. Okay, and this is y is equal to 0. What is this? At time t greater than 0, the lower surface y is equal to 0. At this lower surface y is equal to 0, you can see here this is time 0, this is time less than 0, this is after some time elapsed. At a time greater than t, that means greater than 0 here, what at the surface bottom plate, the mass fraction of the helium is equal to WA naught. You can see this WA naught, WA naught, and WA naught. Okay. This latter quantity is the solubility. Now, this WA naught will tell us about the solubility of the helium in the silica. As the time proceeds, what will happen is that at the bottom plate, W will become equal to WA naught, and at the top surface, at this top surface, WA will be equal to 0. As in your figure. Okay. Now at the steady state, the same what you call the mass flow, that means this mass flow, that means mass fraction of the helium in the positive direction is described by this equation. Okay. This is proportional to the mass flux, the mass flow rate of the helium per unit area is proportional to the this particular mass fraction difference divided by the plate thickness, and there's a rho and the proportional to constant dAB comes into picture. This can be replaced with J is equal to minus rho dAB dWAB dy when we consider a small element, a small element in between the, that means if I consider a plate like this, that means if I consider the small portion here dy, then we can write this equation. This is known as Fick's first law of diffusion. Okay, we'll come back in the next session and we'll go further in the topics.